I'm still waiting. 17 are there. Okay, so now let us start the lesson. So we talked about the notion of increasing and decreasing function. Actually, it was an informal discussion. So now that you have the idea what is going on, I want to go back and review everything, but now this time in a formal way. Yes. So first we start with the definition of an increasing or a decreasing function. Okay. So when we say that a function is increasing, so do you remember? So when I say that a function is increasing, it means that if I look at the graph of the function, yes, something like this, when I go to the right, the values of the function are becoming greater and greater. Yes, they are increasing. So this is convention. When we say that the function is increasing, the convention is that when I go to the right, the height of the function is going higher and higher. Of course, it is clear that if I go to the left for the same function, the height is going down. So when we say that a function is increasing, it means that whenever we start moving on the x-axis, and then we see that the height of the graph is actually getting higher and higher. Okay, so what does it mean? It means that if I look at 2 points, x1 and x2, so that x1 is less than x2, if I look at the height of this function, if this is the graph of my function f of x, the height of this one from here to here is f of x1, and from here to here is f of x2. So this means that when x1 is smaller than x2, and if the function is increasing, then it means that f of x1 is also less than f of x2. Okay, so that's a formal definition of an increasing function. And then we can say that this function that you see is strictly increasing. I will come back to it because when I check the book, there are 2 different words for that. And this is usually, of course, common. Okay, so I would say that definition, a function f is said to be strictly increasing on an interval I. So you know that what an interval is. So for example, when I say all the values between 1 and 5, this is called an interval. Yes. So interval on the x-axis. So any interval with different points here. A function f is said to be strictly increasing on an interval I if, so you know that this symbol means for all x1 and x2 in I. If x1 is less than x2, then f of x1 is also less than f of x2. So you see, that is exactly, this is a rigorous definition of an increasing function. This gives you the same idea. When my x1 is less than x2, the height for this point corresponding to x1 is less than the height corresponding to this point. This is the meaning of increasing function. Okay, and when I say, I will talk about this, what is this adjective here or adverb we are using, is strictly increasing. Okay, and then a function f is said to be a strictly decreasing on an interval I if, again, for all x1 and x2 in I, if x1 is smaller than x2, let us see what happens. We learned about what is the meaning of decreasing function. Let us just understand it pictorially. So here I have a function which is going down when I go to the right. So then what happens? Then it means that if I choose x1 and x2 here, so that x1 is less than x2, then if I look at the height corresponding to x1, this would be f of x1, and then this would be the height corresponding to x2, so that would be f of x2. So this time you see that when x1 is smaller than x2, f of x1 is greater than f of x2. So this means that a function is decreasing if x1 less than x2 implies that f of x1 is greater than f of x2. Okay? So if you increase the value of x, the value of f of x also increases, the function is increasing. If you increase the value of x, the value of f decreases, the function is said to be decreasing. And if you remember, we connected the notion of increasing and decreasing to the derivative, because derivative is possibly the simplest way to understand this behavior regarding a function. But some functions are intuitively clear what type of them are there. Yes, for example, if I ask you what type of function, even if you don't know the graph, if I give you f of x is equal to, f of x is equal to x, is this function increasing or decreasing? First of all, you might have the idea how to draw the graph of this function. So you can immediately see that the graph of this function y equals to x is just this bisector. Okay, so this is the x-axis. So you see immediately when I start going to the right, the height is actually increasing all the time. So you can immediately conclude that this function is strictly increasing. Or let us look at it at the other in a different way. I would say that, is it clear for you, when I increase the value of x, the value of f of x is also increasing, because f of x in this particular case is x itself. So it is clear that when I increase the value of x, the value of f of x also increases. Yes? So it is clear. This function is increasing. And then let me give you another example. F of x is equal to x cubed. Is this function increasing or decreasing, or none of them? It's clear that, again, by just definition, you don't need to know any derivative at all. Immediately, it is clear that this function is increasing, strictly increasing. Why? Because if I start increasing the value of x, the value of x to the 3 also increases. So this is an increasing function. Okay? But for example, what do you think about this? F of x is equal to square root of x. This function also is increasing, yes. It's clear that the type of this function is in a way that when I increase x, the value of the square root of x also increases. So all of these functions are increasing functions without connecting this idea to the notion of derivative at all. Just using the idea, what is the meaning of an increasing or decreasing function. But let me, for example, consider this function. F of x is equal to x squared. Is this function increasing or decreasing? Yes, it is not clear. You might say that, okay, this function is also increasing because if I increase the value of x, the value of x squared also increases. Yes, this idea is correct, but if you limit yourself to the positive values of x, if I limit myself to the positive values of x, then of course, when I increase the value of x in the positive part, then x squared is also increasing. But if I go to the negative values, if I choose a negative value, for example, -4 is a negative value, -3 is also a negative value. Which one is a smaller? Definitely this one is a smaller. -4 is smaller than -3. But when I square it, this becomes +16 and this becomes +9. And then it means that +16 is greater than +9. So this means that, yeah, you need to be careful that this function is increasing. Might be this idea is intuitively clear that, okay, if I increase the value of x, x squared also increases. Yes, if x is positive, but it is not completely generic. So this means that the behavior of this function is not clear. It is actually two-folded behavior, yes? If x is positive, when I increase the value of x, the function increases. But if the value of x is negative, when I increase the value of x in the negative part, the value of the function actually goes down. Okay? So this means that this function is decreasing on the negative part and increasing on the positive part, which is clear even from the graph of the function. Do you remember? The graph of the function f of x equals to x squared is like this. When I am in the negative side of the x-axis, the function is actually going down. The graph of the function is going down. And then immediately when I go to the positive one, the value of the function is going up. So this function is actually going down on the negative side and going up on the positive side. So be careful about these points as well. So for example, what do you think about this function? F of x is equal to 2 to power x. And what do you think about this function? Is this function increasing or decreasing? Or it has different behaviors? Any idea? Think in this way. If you start increasing the value of x, what will happen for the value of 2 to the power of x? If it is increasing all the time, definitely it is increasing function. If it is decreasing all the time, it's of course a decreasing function. But if it behaves differently in different intervals, so that function is not a monotone function, by the way. So let me also teach you this word, monotone. So it means that it is either increasing all the time or decreasing all the time. So we call it a monotone function, yes? Monotone means either increasing or decreasing. Always. Okay, so that's also some word that is good to know, monotone functions. So here, this function is a monotone function from which type? From increasing type. This function is a monotone function, increasing type. For example, if I give you this function, f of x equals to x to the power minus x to the power of 3. So then definitely it is clear for you this is a decreasing function. Why? Because if I start increasing the values of x, because of this negative sign, the whole expression starts going down. So that is a monotone function, but from the decreasing type, yes? So it's a monotone function decreasing all the time. Okay, let us go back to this problem. What do you think about 2 to the power of x? No ideas?
It's increasing.
It's increasing, yes? Because if I start increasing the values of x, if I make the exponent of this exponential function more and more, of course, it becomes clear that the value of the function becomes actually bigger and bigger. Okay, so what I wanted to say is that, do you remember last session I was connecting this idea of increasing and decreasing to the notion of derivative. Still, I want to come back to that lesson because I want you to understand the connection between them. The reason that is better, because if the function is more complicated and more involved and have a mixture of behaviors, in some interval it's increasing, in the other interval it's decreasing, keeping track of all these odd behaviors for a complicated function using the idea that I am just describing is hard. Okay, so don't misunderstand. If you have some, for example, let me test your understanding again. What do you think about this function? Do you think that this function is a monotone function? So you see, if I ask you to take the derivative of this function, you have to wait until math 4 because you don't know how to take the derivative of this one yet. But you are still, it is possible for you by understanding the definition of monotonicity here, you can immediately see that is this function increasing or decreasing? What is your guess for this function now? It's decreasing, exactly. Because if I start increasing the value of x, the denominator of this expression becomes bigger and bigger, and the numerator remains constant. So if the numerator remains constant and the denominator is growing, it's completely clear that the whole fraction is going down. So this is a very important tool. So understanding the definition is also very important for you. Let me just repeat. This function, you cannot use derivative at the level of matrix C to understand that this is increasing, but actually you don't need it at all. Yes, even I don't do it if I want to see if this is increasing or decreasing, because I know how to differentiate this, but it takes time. But immediately by looking at this function and understanding the definition, I immediately realize by increasing the value of x, the whole value of the function is going down. So this function is a monotone function. And what is the type of this monotone function? It's decreasing. Yes, is there any question? Okay, so the understanding the definition is extremely important. Then, of course, the reason that I want to connect this idea to the notion of derivative, because that is more practical. We have functions that are not all the time, they are not monotone functions usually, and it is not easy to see on which intervals this behavior happens, that when I increase the value of x, the value of the function increases, and when I decrease the value of x, the value of the function, or go down, sorry. What happens on which intervals if I increase the value of x, the value of the function goes up, and on which intervals when I increase the value of x, the value of the function goes down. Because of this complex behavior, this is not a practical way. But whenever you can use the idea, just use it. Okay. One thing before leaving this, I want to talk about this strictly increasing or decreasing. It's because sometimes our functions are simply called increasing or decreasing. I want to make to draw a picture for you to find the difference. So if a function constantly goes up, for example, like this is called strictly increasing. But you might have a graph like this. It increases at some point, it becomes flat, horizontal flat at some other point, so for some interval, and then it goes up. So what is clear, I cannot say that the value of this function is increasing all the time. No, it is increasing up to here. It doesn't go down, but it doesn't go up either here. it remains constant, and then again it goes up. So if I want to differentiate between these two behaviors, I would say that this is strictly increasing, and then I would just simply say increasing here. Okay, and the same is true for a strictly decreasing and decreasing. Okay, of course, when you say a function is strictly increasing, it's also clear that this is also increasing, but not the other way around. So if I want to just remedy a little bit this definition, if I want to take this adverb out from this definition, then I would say that if x1 is less than x2, then f of x1 is less than f of x2 or equal to f of x2. So you see here, if x1 is here, if this is x1 and this is x2, x1 is less than x2, this height is also less than this height. But now let us change the idea. Let me take this one to be x1 and this one to be x2. Here again, x1 is less than x2, but f of x1 is equal to f of x2. So if this happens, that if when x1 is less than x2, then f of x1 is either less than f of x2 or at most equal to it, then instead of saying it's strictly increasing, I just say that this is increasing. And the same thing here, if I put this equality here, that would be the same idea for the decreasing function. Okay, any questions so far? So these are, I think I understood the Swedish correctly. They differentiate between these two behaviors, and that's completely common. Okay, now this is a formal setup for the definition of increasing and decreasing function. Now I want to start repeating what I had, what I presented in the previous session, and I want to connect the idea of this being monotone to the notion of the derivative. Okay, so, and that is the geometric picture that you need to have in mind, okay? Because the rigorous mathematical proof for these needs more advanced theorems that is beyond the scope of this, the high school actually lessons, okay? So, but understanding them from intuition is very, very simple. Intuitively is very simple. So here, everybody knows that if the function is going up here, what is happening? The function at this interval is going up all the time. So what is the common property of this part of the graph? So from geometrical point of view, it means that if I take any point on the increasing portion of the graph, and if I draw the tangent line to that graph, I hope that you can immediately convince yourself, at this level is enough to convince yourself like that. So you see that even though the slopes are all different, but all of them are in this type of directions. And you know that that is k positive. So it means that a slope of all these tangent lines at the points where the points lies on the increasing portion have different slopes, of course, but it is easy to understand that all of these slopes are positive, okay? But from our previous lesson, we know, for example, if this point is point A, if I ask you what is, let me call it K1. So if I ask you, how do you calculate K1? If this function is the function f of x, you say that K1 is equal to f prime of A. On the other hand, by looking at the geometry, how it is inclined, you understand that this is positive. So this means that f prime of A is also positive. The same reason can go for this point, all of these points. So if I take this B and then I give you this is K2, then f prime of B is K2. But of course, we know that K2 is positive because it is inclined in this direction. So hopefully you see that this is a very nice analytical tool in our hand so that we can realize which part the function is increasing. The answer is simple. If the derivative the function is increasing at those points, on those intervals on which the function, the derivative of the function is positive. So you need, this is more important tool in our, more powerful tool in our hand, yes? So remember, increasing means the derivative is positive. And then, of course, hopefully, let me just draw one picture here. If the function is decreasing, and then if I take any point, it doesn't matter which point, if I draw the tangent lines, all these tangent lines are inclined in the other direction in which the slopes are negative, yes? So this means that you need to have in mind decreasing is related to the derivative negative. So the derivative, if the derivative at a point, at the points on an interval are all negative values, it means that my function on that interval is decreasing. And if it is positive, it means that it is increasing. And then let me make sure this property of increasing and decreasing is not related to one single point. Okay? I cannot ask you, if I give you a graph, I cannot ask you what is the function, what is the function increasing or decreasing at this one single point? This is meaningless, because increasing and decreasing, it means that I need to have two values, comparing them together so that to see which one is bigger and which one is smaller. So be careful. I can ask you, at this point, what is the slope? This question is meaningful. What is the slope of the tangent line at this single point? And then you can, for example, see that this point, the tangent is positive, so it means that this is in this direction, you say that the derivative is positive. But I cannot say that, is the function increasing at this point? No, increasing in a relative behavior. So you need to compare it with something else to see how the function is behaving. Is it going up or down? By one single point, I cannot answer that. Okay, so that's also something I want you to know. Any questions so far? Okay, so this is very important. Have this picture in mind. If you forget which one is which, you shouldn't be worried. You just imagine this picture and then immediately realize what is going on. Now I want to start practicing on this one with a little bit more with the functions which are not very clear from the beginning. Which type of functions are they? Okay, so now this example that I want to bring up is probably one of the most important examples. You need to know this example very, very good. Okay, so let me write for you here. If you have any questions, of course, let me know. Example. Determine the intervals. Let me write interval or intervals because it's not clear how many of them are there. Determine the intervals where the function is strictly monotone. Okay, let me write increasing or decreasing. Okay. Let me start with a very simple one. So here, f of x is equal to 2x squared plus 3x minus 4. Okay, so here I want to see on which intervals is this function is increasing and the other one is decreasing. Okay, so you see this is a little bit, this has an odd behavior because it is not clear if I increase the value of x. Of course, it is clear that if x is positive and I start increasing the value of x, the value of the function also goes down. but it is not clear that the border is exactly positive and negative. Might be the border should be somewhere else, yes? And then this is actually the case. Let us see how it happens. So the reason that I am talking about this, because I want you to understand, even though this idea is completely correct, but sometimes it is not easy to apply it, okay? This is one of those cases, even though this function is one of those very simple functions. Yes, it's a quadratic equation, a quadratic polynomial. If you see this question, this type of question, you need to remember, you need to take the derivative first. This becomes 4x, this becomes positive 3. Okay, so this is your derivative. And then you remember that if the derivative is positive, then your function is increasing on those values for which, on that interval for which the derivative is positive. Okay, so I would say that f is increasing or is strictly increasing. Let me write si, s dot I is strictly increasing if and only if the derivative of x is positive. IFF means if and only if. And by the way, if you remember in the previous session, I talked always in your lesson, we are talking about those functions which are differentiable and continuous. Continuous means that I can draw it with one pen stroke, and differentiable means that there are no sharp points in the graph of the function. Okay? So this is always, you should have it in the back of your head, okay, in this discussion. Okay, so now it means that f prime of x is positive. So this means that 4x plus 3 is greater than 0. So this means that 4x is greater than minus 3. And then this means that x is greater than minus 3 divided by 4. So it means that if I choose x greater than or equal to minus 3 over 4, the derivative is positive, and when the derivative is positive, the function is increasing. Okay, so I would say that, and of course, when the derivative is negative, if this is the case, the derivative is positive. If you want to, you can say that f is strictly decreasing, SD, if and only if f prime of x is less than 0. So this means that f prime of x less than 0, this tells me that 4x plus 3 is less than 0. This means that 4x is less than minus 3, so this means that x is smaller than minus 3 over 4. And then how you need to write the answer is this. Yeah, so you see, I would write that the function f, let me write f is increasing, strictly increasing on the interval. You need to write x greater than or equal to 4 over 3, 3 over 4. Yes? And then f is strictly decreasing on the interval x less than or equal to minus 3 over 4. The reason that now when I want to write the answer, I am including this minus 3 over 4. You see, I am putting equality because it doesn't matter. Because you see, the function is behaving like this. I don't know the exact graph, but assume that here is minus 3 over 4. I don't know, if you put minus 3 over 4, what happens here? So this becomes 2 times 9 over 16 minus 9 over 4 minus 4. So it becomes 9 over 8 minus 18 over 8. And then minus 32 over 8. So anyway, it's a negative number. That is enough for me. So for example, assume that this is the case, and then you draw the graph. Of course, it doesn't exactly passes through the origin. If I put x, it passes through negative values, it goes like that. This is minus 4. This is just exaggeration. That is not my point. Okay? So you see that I saw that the function is decreasing before this, and that is correct. If the function goes down up to this point, and then after that it goes up. The reason that I am including this both on the left and on the right, because I told you that behavior of increasing behavior or decreasing behavior is not for one single point. So if I write x greater than or equal to minus 3 over 4, if I just write this and that, then people might say that, okay, what happens with one single point? Okay, but I am telling you that from minus infinity up to this point, including this point, the function is going down. And then again, starting from this point to the right, the function is going up. This is the reason that I am putting these equalities there. Any questions? Okay, but all these information are encoded in, we can write it a little bit nicer. How? We can say it like this. We can draw a table and put x and xf prime here. For the time being, this is enough. And then you take the derivative f of x. Instead of solving inequalities, which would be hard for you, this was easy because this is a first degree inequality. So we know how to solve it. But if this is a quadratic inequality, this is not at the level of your lesson how to call it. And even if this is higher inequality, even I don't know how to solve it. Okay, so we need to have a better trick and technique. How is that? Instead of making it positive and negative, I put it equal to 0. Okay, I take the derivative, and instead of writing all these things, even though they are completely right, I put the derivative equal to 0. And then what I get 4x plus 3 is equal to 0. The answer is, as before, minus 3 over 4. Then I put minus 3 over 4 here. Of course, when it is minus 3 over 4, the derivative becomes 0. That is clear. Yes? But now, I want to see what is the sign of the derivative before that and after that. This I want you to understand. Of course, you can just memorize it like that, but I want you to understand why this method works. First, let me tell you the method. The method is this. Choose a random number, whatever you like, which is smaller than minus 3 in this area. Okay? And the easier, the better. Yes? So which one is more suitable? I would say minus 1. Yes? I take minus 1 and put it back in your derivative. 4 times minus 1 is minus 4, plus 3 is minus 1. Minus 1 is negative, so I will claim that this will remain negative all the time. This is strange, yes? Because I just checked the sign of derivative for one single number. But how many numbers are smaller than minus 3 over 4? There are infinitely many. So how is it possible to conclude that this will remain negative whatsoever? You don't need to be worried about that. I will come back and talk about that. But I'm just teaching you the trick now. Okay? And then choose a number after this. The easier, the better, yes? Because you have to calculate something. It is clear 0 is the best choice, yes? Take 0 and put it back into the derivative. It becomes positive 3. And then you are relieved that this is always positive. And then you just need to, you see, this is the symbol we use. On these parts that the derivative is negative, this is the symbol we use, an arrow going down. So the function is decreasing, and this one, the function is increasing. And of course, I would say that before minus 3 over 4, this is the x-axis. It goes from minus infinity to plus infinity. This means that before is smaller than minus 3 over 4. This is 3 over 4, and this is after minus 3 over 4. So this is enough. It is clear for me now that before this, the function is decreasing, and after that, the function is increasing. So this, you learn this technique. This technique will not work if the function is not continuous. Okay? But as I told you that in this chapter, and mainly even in Math 4, we are dealing with continuous functions. So this is completely reliable. But I want you to understand why this method works. Why, when I choose one single number from here, check the sign of the derivative, I can be sure that this will remain negative for all infinitely many values that I haven't checked. Okay, this I want you to understand. Okay, so to understand that, let me draw a picture for you. Assume that you have a continuous function. So a continuous function, it means that that is a continuous curve that I can draw without any pen stroke. If the function goes like this, okay, there is no intersection between the graph and the x-axis. So it means that this function, let me call it g of x. So this function, if I ask you how many roots are there for this equation, you would say nothing, because this curve does not intersect the x-axis. Okay. So, but now assume that you have a continuous curve that actually cuts this graph somewhere, and it goes up after that. Here, it also goes up before that. Okay, so assume that this is your graph. Now, if I ask you, what is this equation? What are the solutions of this equation? You would say that the x-coordinate of this point, let me call it A. The x-coordinate of this point, let me call it B, C, and D. These are the solutions. Okay? And now I am telling you something. If you have two roots, between two consecutive roots, yes, if the function is continuous, between two consecutive roots, the function is entirely negative. It's below the y-axis, below the x-axis, or it is entirely positive. Yes, I hope that I could convince you. Yes, because if I want to draw this, yes, if the function is discontinuous, I can expect this behavior. Yes, this function goes down and then suddenly jumps up and then again goes down. You see? These are two consecutive roots of this equation, but there is no guarantee that the function is always positive or negative, because you see that one portion of the graph is below the x-axis and one portion of the graph between these two roots is above the x-axis. So continuity is actually very essential in this argument. Okay, if I have a continuous function, and if I have some roots for this equation equal to 0, then if you look at if you look at the interval between consecutive roots, then what happens? Between the consecutive roots, either all the graph lies below or all the graph lies above the x-axis. So this means that if I just randomly choose any number between these two, and I check the value, in this case, if this value for that random number chosen between A and B is negative, this behavior remains the same between these two numbers. Yes, it doesn't matter if I have chosen this, I have chosen this. Of course, the values would be different, but still both of them are negative. And I hope that you can convince yourself easily that it is independent of my choice for these points. As soon as I am choosing these points between these two consecutive roots, and if one of them turns out to be negative, all of them will be negative. So this is why, you see, this function f prime is this function. Remember, polynomial functions are always continuous everywhere. So 4x plus 3 is a continuous graph, and then this idea will work for this function. So it means that if I choose one random number before that and it turns out to be negative, it remains negative whatsoever. It doesn't matter which number I am choosing. So I want you to understand, but if you don't like to understand very details, it's confusing for you, forget about that. But learn the technique. This is the technique that the book is using. I don't know if they have explained this or not, but this is the idea. Okay? Any questions here? Okay, so here you see, for example, between these two, if I choose one random point and I calculate the value of that function, it turns out to be positive, then by this intuitive idea, it is clear that it doesn't matter which points I choose, all of them turns out to be positive. So which one I am choosing for representative is no matter, actually, it doesn't matter. Yes, all of them are completely correct. But of course, for example, I can choose minus 100 here, but why should I? Because minus 1 is easier to calculate. So I try to find the best choice for my calculations. Okay, so any questions so far? Now I try to teach you everything that is needed, but now you start to increase your techniques and be skillful and do things quickly. Okay? Well, let us solve more examples. So I will not explain anything. I just follow the algorithm, what I told you here, especially this one. So I will follow this. Okay, so let me give you another question. Number 2. F of x is equal to, let me write this, x to the 3 minus 6x squared. Okay, so let us do the same problem here. I want to see on which interval or intervals this function is increasing and on which one of them it is decreasing, if any. Okay, we learned that we need to do the derivative. So the first step when you see this question is to take the derivative. When you take the derivative, it becomes 3x squared minus 12x. Okay, be careful. What is the next step? In principle, the next step is to put it positive and solve it. To put it negative and solve it, then it would be a lot of problems for me. But I told you, instead of doing that, let us do a trick. I put it equal to 0, even though it seems strange, yes? I put it equal to 0, and then I will try to solve an equation which is easier than solving an inequality. What type of equation is this? It is a quadratic equation. You can use ABC formula or PQ formula. But in this case, there is a much simpler method, and that is to factorize 3x out. So let us do that. So then this implies that 3x, I factor 3x out, it becomes x minus 4 equals to 0. Then by zero product rule, either x is equal to 0 or x is equal to 4. Then I put them in the box not to forget about them, and then I go and set up a table. For the time being, this table has only 2 rows. One of them is x, one of them is f prime, and then you put these numbers that you found here in front of x, but you have to keep the order. The left one on the left, the smaller one on the left, and the greater one on the right. So I will write 0 and 4. If I ask you what is the value of f prime when x is equal to 0, it is clearly 0. Why? Because I myself equate the derivative equal to 0, and I got these 2 answers. So it is clear that if I put these numbers back into my derivative, the derivative becomes 0. You don't need to really calculate, but if you want to, you can do that. Okay, now I want to see is part positive or negative. I want to determine the sign, positiveness or negativeness of my derivative for values smaller than 0, for values between 0 and 4, for values greater than 4. Yes? But I want to use this trick. Can I use that trick? Yes. Why? Because my derivative is this expression. This expression is a polynomial. Every polynomial is continuous everywhere. So something like this argument will work. Okay? So if I want to see what is the sign here, I choose a random number less than 0. Of course, the best choice, I would prefer to choose -1, yes? Minus 1, where I should put it? Don't be confused. You're not allowed to put it here. You see, this is the row for f prime. So whatever you want to write here in this row should be answered through y prime. Sorry, through f prime. So I take that random number minus 1 and put it here. So you can do it in a scratch paper even. Minus 1 to the power of 2 is 1 times 3 is 3. Minus 1 times minus 12 is positive 12. And I don't even care to calculate because my point to see if it is positive or negative. So this is positive. Okay? And then between 0 and 4, another time, choose a random number. 1 is the best choice, I think. Put 1 back here. It becomes 3 minus 12. It is negative. So I can make sure that this is negative all the way around, okay? And then a random number after 4, for example, 5. 5 to the 2 is what? Is 25, 30, 25, 75. Yes, and then this is 60. Again, this is positive. So the function is going up here. The function is going down here. The function is going up there. But if you want to be precise, I would say that this function is strictly decreasing on this interval between 0 and 4. It is strictly decreasing on the interval 0 equal 4. And it is strictly increasing on 2 intervals, not 1. Once here, once there, yes? And it is strictly increasing on the intervals x less than 0 or equal to 0 and x greater than or equal to 4. So you see, after 4, it's positive, it's increasing. Before 0, it's positive, it's increasing. Between 0 and 4, it's negative, it's decreasing. You have to write this at the end so that I can realize you have understood it correctly. Any questions so far? Okay. Let me give you another example. This type of examples are also good, and I have seen it in the course book, in this Origo book. Yes, I think they are nice problems. Similar. I don't know if that's exactly this one, but let me ask you something like that. Do you have any questions here? I don't know. Should I give you one more? Yeah, at least I think that's a good idea. Let me, of course, I haven't seen questions except polynomials in your book, but still you can do better. You have studied a little bit of other functions that you can differentiate. Let me give you some of those examples before leaving this lesson. Okay, so number 3, I'm telling you again, these polynomial functions are the only functions that you can see in the book, but there is no downside for writing this one as well. So f of x, for example, is equal to e to the power of 3x. So this is one of those problems. If I give it this to you in the exam, by the way, if you are smart enough, you can completely avoid everything that I told you here. Because what do you think about this function without any calculations? Do you remember the question is that on which interval or intervals this function is increasing and on which one of them this function is decreasing? I'm waiting for your answer, okay? Of course, I will go through this calculation because I want you to see that what you understand intuitively squares with your calculations as well. Do you remember this E? This is the Euler number, yes? 2.72 something, yes? How do you answer to this question without calculations? No idea?
Just differentiate.
Yeah, differentiation, I know, I will do that. But except differentiation, did you forget everything that I talked about in the beginning of the session according to the definition of increasing and decreasing functions? Yeah, okay, so let me repeat. This function is definitely increasing everywhere. Okay, so why? Because I told you, it is guaranteed. The behavior of this function is so simple that I really don't need to take the derivative and get involved in these long arguments. My goal is to see if this function is increasing or decreasing. It means that what happens if I start increasing x? It's clear, if I start increasing x, this is an exponential function. When I increase the value of x, the exponential function increases. Yes? That's clear. So this function is increasing on R, the whole real line. So if you draw the graph of this function using GeoGebra, you see that when you start moving from the very, very far left to the very, very far right, all the time function is increasing. Sometimes it is increasing very small, but immediately it becomes exponentially big. Yes? So this shouldn't be hard to catch it. But let us see if we don't catch this idea. If you, by the way, you write this in the exam for this function, that's completely okay with me. Okay? Because the goal here is to see where the function is increasing and where it is decreasing. But let us follow this method. So what is the first step? Okay, now tell me, what is the derivative? I want to see that, are you with me or not? What is the derivative of f? Everyone? Hello? Are you there or not? I can see that you are 30 here.
Is it 3e to the power of 3x?
Yes, 3e to the power of 3x. Okay, tell me again. Don't mute yourself. What is the next step? The first step is to differentiate. We did it. What is the next step? Tell me. Hello? What is the next step?
Calculate the x value.
Okay, so how? Putting it equal to 0. Okay, can you tell me what is the answer then? I put this equal to 0. What can I conclude? Of course, I divide by 3. So what is your answer to this equation? E to the 3x is equal to 0. Are you with me or not? Let me make it simpler for you. Can you solve this equation for me?
I think 3x is...
Yeah, momentarily forget about that. That might be...
to ln of 0.
Okay, ln of 0 does not exist. Do you remember I told you that ln of positive numbers exists? So that's correct. Some idea is to write 3x is ln of 0. But if you remember, if you go back to the lessons, I told you that when I want to have ln of something, that something has to be positive strictly. So it means that ln of 0 is not defined. If you don't believe, you can just use your calculator, type ln of 0, you get some error message at the end. Okay? But, so what is the problem? What does it mean? It means that there are no solutions. It's simple. I don't know, you need to lubricate your brain a little bit. So you don't try to use your memory. You know this knowledge. 2 to some power is supposed to be 0. Is there any value for x so that 2 to that power becomes 0? Yes or no? Yes or no? Okay, so you are not cooperating. Let me answer myself. There is no number that if I put instead of x, 2 to power x becomes 0. The same story is true. E to power 3 times x is not equal to 0. So this means that there is no solutions. No solutions. Okay? So then what should I do? I should draw a table. Unfortunately, this table is completely empty, more or less. I put x, I put f prime here. The values that I am supposed to put here are those values that I get when I put equal to 0 and I get answers. But when I put this one equal to 0, I do not get any answers. So nothing is up there. Okay, then what? Then it means that I should choose a random number here. What is here? It goes from minus infinity to positive infinity. Sometimes people emphasize this by writing this. It's a good idea, by the way, to write minus infinity here up to positive infinity so that you can see that it goes from minus infinity to 0, it increases to 4, it increases to plus infinity. But if I do not have any roots, I put minus infinity, I put positive infinity, but there is nothing in between, which is important. Okay, then it means that I can choose any random number that I like. Why? Because the exponential functions are also another class of continuous functions. Okay, so that's a class of continuous functions. So it means that I choose a random number and I put it here and determine the sign of my derivative. What is the best random number that I choose? I would choose 0. If I put 0 here, e to power 0 is 1, multiplied by 3 is 3, 3 is positive. So this means that this is positive all the way. And this means that this function is increasing everywhere. And that squares with our intuition about this based on just definition. So you see that that definition was much more quicker here. Is that understandable? Yes or no? Okay. I don't know why do you hesitate to talk anyway. So I think the best job for you is to be a math teacher because you talk a lot. Okay. Let me give you another example. What do you think about this? Let us practice a little bit. I will not teach more probably, but I want you to understand these things. These are very, very important. By the way, these concepts, if you want to go to technical universities and any engineering program, these are with you until the end when you graduate. Yes? These are under the title of calculus course. So calculus is an extremely important tool for any engineer. If you go to science programs, of course, you need to study much, much more than this. Science program like mathematics, physics, a little bit of chemistry, and then, of course, computer science. So electrical engineering, you really need to know very, very well these things. So I want you to pay attention to it because at the end, you have to have them in you. And by the way, I don't know why the book hasn't talked about these type of functions in this part, because they are completely at the level of your lesson. You can take the derivative, you know how to solve exponential functions in principle, yes? Okay, let me just give you another example here. So g of x is equal to, let me write something here for you. 5, let me make it simple. 5 minus e to power x. Okay, I ask you on which interval or intervals this function is increasing or on which this is decreasing. Okay, talk to me. How do you think about the problem? Do you think that we can just immediately answer that without calculations? If yes, please explain it. And then if that is the case, I still want to use the calculations to confirm our answer. Do you have any idea what is the behavior of this function?
It will be decreasing.
Okay, can you, Martin, explain how did you come to this conclusion?
Because the higher the x value is, the lower the y value is.
Exactly. Because if I just give you this part, it is clear that when I increase the value of x, e to the power of x becomes bigger. But my function is not this. My function is 5 minus that. So it is clear that when I start increasing x, this part increases, but 5 minus that part, because this part is going up, the whole expression goes down, yes? So this means that it is not hard to see at all. It doesn't need any calculations. This function is a monotone function. And what type of monotone function? Strictly decreasing. Okay, so this is very easy. It's much easier than calculate. So this is why I'm saying that understanding these concepts are important, because sometimes you can find a way out of it. If the calculations are messy, you really don't need to calculate. But I want you to also learn the algorithm that I told you. Let us do this. The first step is to take the derivative. I hope that every one of you can do the derivative immediately. I have the difference of two functions. This is the constant, that the derivative is 0, minus the derivative, and that is the most famous function, whose derivative is equal to itself. Okay? So if I simplify that, it is just simply minus e to power x. The next step is to put this one equal to 0. And then this, what does it mean? It means that minus e to power x is equal to 0. I multiply by a negative sign. It becomes e to power x is equal to 0. Again, can you tell me what is the answer here? What is the x value here? The x value is?
It has no real solution.
Yeah, no solutions, yes. No solutions. Thank you. Okay, what you do, you just draw the table, you put x, you put g prime here, because the name of my function is g. It's better to put it even though it is not written in your book. By the way, this is a symbol we use for plus, for infinity. It's just like 90 degree rotated, okay? And minus infinity, positive infinity. Okay, there is nothing that I can put here because no solutions. So I can choose whatever I like randomly from this interval. Why I can do this? Because exponential functions are also among the famous category of continuous functions. And this random choice highly depends on this continuity property of a function. Okay, so I'll put randomly, I put 0. The best choice between minus infinity and positive infinity is 0. Where should I put it? G prime. What is G prime? G prime is this guy. If I put 0, which I chosen randomly, e to power 0 is 1, but I have a negative sign, it's minus sign. But then I told you that because this is continuous, this means that this is negative all the time. And then this means that this is decreasing. And as Martin predicted, and I also explained it for you, that it squares with our intuition about the problem. Yes? Yes or no? Okay, let me make it a little bit more challenging. I think these are really important things that you need to understand. Okay, so let me give you, of course, again, this is not in the book, but I don't think this is hard for you not to understand it. So let me write this function. F of x is equal to, so these last 3 examples, you can take it as optional if you want to. Don't worry about it in the exam, but I really want you to learn, okay? Because I know you have good experience, you have good talent actually. This class has a good talent in mathematics, so why not? You should be able to learn these things. Okay, so here I give you this function. And I want to see if this is increasing or decreasing. This is a little bit hard because if I say x is increased, what happens to this? Because if x is small, then might be this dominate that one. If x is big, this will dominate that one. So it is not clear what is going to happen. So it is not that easy to guess the behavior of that function. By saying that, okay, I increase the value of x, what happens to the whole function? Is it increasing or is it decreasing? Sometimes going up, sometimes going down. Another thing that might be your book hasn't talked about this is because the domain of this function is not the whole real line. For example, can I ask you what is f of minus 1? The answer is no, because if you put minus 1, this is no problem. But if you put minus 1 here, square root of minus 1 is not defined. Okay? And by the way, all these analysis is called real analysis. Might be I should emphasize that, yes? So the notion of derivative, limits, I don't know, increasing, decreasing functions are all on the set of real numbers. If you want to study the complex analysis, then of course that is the beyond the scope of, so you need to go to some majors in the university, including mathematics, physics, or other electrical engineering to understand the complex analysis. So what I am talking about, don't say that what happens in minus 1 in the complex numbers. No, we are just studying real analysis. Okay, so here, this thing, there is a limitation. I didn't have this limitation before. All those functions that I presented here, they doesn't have any limitation from the value of x point, from the x point of view. Yes, I could fit any number to the function as I like. This is the first time that I have some limitations about this. So this will affect the domain of my function. So instead of writing that x goes from minus infinity to positive infinity, I have to be careful, because x for this function cannot take on negative values. Okay? What is the minimum value of x? It is hopefully clear for everyone. That is 0. 0 doesn't make any problem. A little bit smaller than 0 becomes problematic, yes, because the square root of negative values are not defined in the real system. Okay, so it means that first of all, the domain of my function, you remember this is the symbol for the domain, is the interval greater than or equal to 0. Okay, the next step, I want to take the derivative. But you remember, if I have a square root of x and I want to take the derivative, what I need to do is to change the form of the function first. X minus 2x to the power of 1/2. And then I can differentiate it. F prime of x, the derivative of x is 1. 1 over 2 goes down. There is a minus 2 there. 1 over 2 goes down. Then I have x to the power of 1 over 2 minus 1. And then f prime of x is equal 1, 2 times 1/2, they are gone. And this becomes x to the power of 1 over 2 minus 1, which is minus 1 over 2. Now, of course, if this differentiation is the only problem, I don't ask you, if I ask you to differentiate this function in the exam, which is at the level of the book, by the way, if you answer this, that's okay with me and you get the full mark. But here, I want to do something with my derivative. It's better to simplify. So this art of simplifying expression in mathematics, you really need to learn, okay? So what I do, because I don't know, for me, working with negative exponents and even fractional exponents is hard. Working with the square root signs is more manageable for me. So what I do, I will write it minus, I will take it down, it becomes x to the power of positive 1/2, but there is a better name, more familiar name for us, and that is the square root of x. So it's 1 minus 1 over a square root of x, that's my derivative. So let us keep it and box it here. Okay, so now what is the problem here? The problem is that this function is not continuous. You need to be a little bit careful. Why this is not continuous? It is continuous everywhere except when x is equal to 0, which is allowed here, yes? I don't want to go through these details, but you just want to understand the behavior of this function. The first thing that you need to do is to equate it equal to 0. As before, I'm just doing the same thing. Nothing has changed here. The only difference is that I have to be careful that x is non-negative. And when I put this equal to 0, this means that this is equal to 0. And then what happens here? I need to solve this equation. If you remember, I always tell I hate fractions, so I get rid of fractions. I multiply by square root of x. This becomes the square root of x. This becomes minus 1 because the square root of x that I am multiplying will cancel this out. On the right-hand side, 0 times the square root of x is just 0. And then I move it 1 to the right, and then I square it. I get x equal to 1. Is x equal to 1 acceptable? Yes, you can check it. If you put x equal to 1, it becomes 1 minus 1, 0. On the other hand, 1 is positive. Okay, and then if you want to draw something similar for this, you would say that, okay, this is x, but I don't write from minus infinity to infinity. I write from 0 to positive infinity. And then I just found a number here. Okay? And the other difficulty is that I used to put a 0 below it, but this is not 0 in this case. You can check. If I put x equal to 1 back into this function, yes, it is undefined because, oh no, sorry, it is 0. Sorry, I made a mistake. That's 0. Yes, I put 1. Of course, it is clear. I put it equal to 0, got 1, so it is clear that if I put it as 0. But then, when I want to go here and there, I need to be a little bit careful. This function is a little bit a strange function because it is not continuous at 0. Okay, so this part is not continuous because if I put 0, it doesn't make sense here. The denominator becomes 0. But this happens only at this single number. After that single number, this function is continuous. So still I can use the same trick. I choose a random number between 0 and 1 to see what happens here. But the I don't know, might be 1 over 2 is good. Okay, so if I put 1 over 2 here, what happens? The square root of 1 over 2, it becomes negative. If you don't believe me, just put 1 over 2 with your calculator and calculate this. The final answer is negative. And be careful, it is not important to find the exact value. We want to see if it is positive or negative, that's it. Okay, and then this is G, this is F prime. And then bit after 1 up to infinity, let me choose, for example, 2. Then it becomes 1 over a square root of 2. 1 minus 1 over a square root of 2. Okay? 1 over a square root of 2 is smaller than 1. So 1 minus that number is positive. Yes? So this function is decreasing here, and it is increasing here. This was probably the hardest possible, but it was manageable at the level of your lesson. You see, there are some minor points that you need to be careful. This doesn't mean that your math knowledge is not enough to solve this problem. But if I want to answer this question, be careful. You cannot say less than 1 because this is not minus infinity. You should say that on this interval between 0 and 1, it's strictly decreasing between 0 and 1, and after 1, greater than 1 up to infinity, it is strictly increasing. Is that clear? Okay, so if you don't like these kind of things, you can simply ignore examples 3, 4, and 5. Okay, so 3, 4, and 5 are only for those students who are actually a little bit more interested in the mathematics itself. Of course, if the functions are getting more involved, this analysis becomes harder and harder. And one main theme of real analysis is to understand the behavior of a given function without having, by the way, without having the graph of the function. Because most of these things are completely obvious if you have GeoGebra. For example, please do that at home. You need to be creative. You need to be, how do you say it, active. Active learning is much better than passive learning. Just do this. Let me just finish this. I will come to you. Just draw this graph with GeoGebra. It is a matter of seconds that you can understand this behavior. because you see a graph, everybody, even a primary school student, can immediately see that where the function is going down and where the function is going up. Be careful. The logic is the other way around. The reason that GeoGebra can draw the graph like that, because mathematicians has programmed that by using these ideas. Okay, now Martin, what's your question?
If a function is discontinuous.
Yes, this function is not discontinuous. No, this function is not discontinuous. The function is not discontinuous because first of all, on the left hand side, this is not defined at all. So if you see the graph, on the negative part you don't see anything, but on the positive part you see a continuous curve. So this function is again continuous, but the domain of continuity is restricted to the positive numbers. But this function...
So is it possible to calculate if it is convex or concave?
Yes, of course, but that is not at the level of high school mathematics. So yes, of course. Yeah, we can more or less all these functions, we can just describe them and draw the graph of functions and everything. Yes. I just want to make sure that you understand. If you have GeoGebra available, if you want to understand, if the calculation is hard, so in principle, you can check your calculation by giving this graph to GeoGebra and see the graph of the function and see that if you have calculated correctly. Okay, be careful about this point. No questions? Thank you for listening. So I end this stream. I will be in Zoom if you have any questions. Otherwise, you can leave. Thank you.